So we're going to start talking about compliance opacity monitoring, and that is what we do using the Land 4500 Mark III opacity monitor. But I will also mention non-compliance opacity, where our relatively new product, the 4200 Plus, which was introduced late last year, can be used. It's a less expensive product and can be used in a number of applications. But most of the time, I'm going to be talking about compliance opacity. So during this presentation, I'm going to answer a number of questions that come up regularly. So what are we measuring? Why are we measuring it? Where are we measuring it? Who needs to measure it? What does Land have to offer? And most importantly, for those of you who are our sales channels, what do you need to ask a customer in order to specify and to quote an opacity monitor? The slide, the image on this slide really is an opportunity to discuss the first of those questions, is what are we measuring? We are measuring the density of smoke coming out of a chimney. This is a rather nice old illustration of Battersea Power Station, which at that time was operating right in the centre of the City of London, and was spewing pollution directly into the urban air. That's no longer acceptable. Battersea Power Station is now closed, and it's been converted to an art gallery. And if you ever visit London, I strongly recommend you pay a visit to the Tate Modern, which is in the old power station. It's an amazing building and an amazing collection of art. So a little more detail on what we're measuring. We're allowing our customers, who are generally industrial process operators, whether they be power plants or industrial boilers, we're allowing them to measure something which they are required to measure by the Environmental Protection Agency or by the environmental agency in the country where they're operating. The regulations require plant operators to measure either the mass of particulate matter emitted from a stack, so that would be expressed in milligrams per cubic meter, or the density of smoke emitted, which is measured in percent opacity. And the 4500 Mark III can actually measure either of these, but it is most often used to measure the opacity, which is a measure of the darkness of the smoke. So a quick detour just to look at how a power plant operates. And I apologize if this is old hat to many of you, but I do know that many of our sales channels don't work specifically in the power sector. So I wanted to give an introduction to how a power plant operates. So oddly enough, we start in the middle of the illustration where the coal comes in. It's generally stored for short-term use in a silo. It then goes to a coal mill where it's pulverized and turned into very fine powder. 50 micron diameter particles are typical. The pulverized coal is then transported to the boiler with a stream of air, where it's combined with more air and burned. Clearly that produces a large amount of heat. The heat is used to generate steam, and there are various parts of the boiler where the steam is produced and then heated to extract the maximum heat from the coal. We then move to the left side of the illustration, where the steam turns a turbine, which drives a generator which produces the electricity. Most of what we're interested in happens after the boiler. So the flue gases, which are hot, corrosive, and dirty, pass through various pieces of cleanup equipment before going to the stack. And most often, we will be mounting an opacity monitor on the stack as a way of measuring the darkness of the plume exiting the stack. A little bit more detail on the cleanup system, the emissions control system, which is used on a modern power plant. So in the boiler, some of the ash, the solid non-combustible material in the coal, will drop to the bottom of the boiler, and this is referred to as bottom ash, and this is taken away and is basically goes to landfill. The gases and any fine ash, which is called fly ash, which passes with the gases towards the stack. The flue gases contain a lot of pollutants, and on a modern power plant, these can largely be removed. So the first phase is typically removing NOx, NO, and NO2, and this is done by a process called selective catalytic reduction, SCR, where the flue gases are mixed with ammonia in the presence of a catalyst, and this converts the NOx to water vapor and nitrogen. This has to be done at a high temperature, which is why it's the first process in the flue gas cleanup. Second phase is mercury removal, which is being implemented throughout the United States at the moment, and generally uses powdered activated carbon. I apologize. Which scrubs metallic mercury and ionized mercury from the flue gases. And mercury is a heavy metal and a cumulative poison, and a very large source of mercury in our waterways and in our food is actually the mercury from coal, which previously went up the stack and out into the environment. Then we remove the sulfur dioxide. SO2 is the leading cause of acid rain, and sulfur dioxide is removed either by wet or dry scrubbing, where the flue gases are passed over either dry lime or a slurry of lime and water. The sulfur dioxide reacts with the lime to produce gypsum, which is a main ingredient in plaster and wallboard. So it's quite common nowadays to have a wallboard factory close to a coal-burning power plant, so that the gypsum that's produced in the flue gas desulfurization can be used to produce wallboard right adjacent to where it's being created. And finally, there's either a baghouse or a precipitator to remove the fly ash, to remove the particles from the flue gases before the residual flue gases go to the stack and out into the ambient environment. And in order to know what pollution is being emitted, plant operators are required to monitor the principal pollutants: sulfur dioxide, nitrogen oxides, NOx, carbon monoxide. Nowadays, mercury is increasingly common, and particulate matter or opacity. Now, opacity was really the first pollutant that was taken interest of, because it's a highly visible product coming out of the stack. So you can see billowing smoke coming out of a stack. That's usually a bad thing. Now, a lot of modern stacks, actually, you see condensed water coming out of the stack. That's because these are using wet flue gas desulfurization techniques. But all that's coming out, even though it's a large and highly visible cloud, the main thing in there is water drops, which are harmless. But in older chimneys, where you would actually see smoke coming out. That is either ash from the coal, or if the combustion is going really badly, if you see black smoke, it's actually unburned carbon, which is both an indication of inefficiency as well as a very nasty pollutant. So we're measuring opacity because it's an indication of the amount of particulate matter emitted from the stack. It's an optical measurement, and it's measuring the density of the plume at the stack exit. And there's a legally regulated technique called US EPA Method 5, where a trained observer under defined conditions can look at the stack exit and from the training can estimate the amount of opacity of the stack plume. Now, it's not a very accurate technique. The standard uncertainty is plus minus 7.5% opacity, which is approximately 4 times worse than we can measure with an opacity monitor, but it does define the conditions where we have to make the measurement. So we have to report the opacity at the stack exit, and we have to report opacity measured using visible light related to the sensitivity of the human eye, so that a Method 5 observer can stand and look at the stack and compare their trained estimate of the stack opacity with whatever we're measuring using our instrument. So I'll unmute there and
the conference has been unmuted.
So has anybody got any questions at this point? Okay. Thank you for not having too much background noise. That means everybody can hear clearly. Okay, I'm going to mute again.
The conference has been muted.
When Stephen Hawking wrote his book, A Brief History of Time, the publishers told him that every time he put an equation in the book, he would halve his audience. So I'm always conscious of that. I think this is the only equation you're going to see today. So I hope at least half of you will be still listening after this slide. So the mathematical definition of opacity is the fraction of light that's lost in crossing the stack. So if we have a light source on one side of the stack with intensity I0, and a detector on the other side that measures intensity I, opacity is 1 minus I divided by I0. So on a clear stack with no smoke present, the opacity will be 0%. If it's pitch black, billowing smoke through there, no light gets across, we have 100%. Typical stacks nowadays have very low opacity, typically less than 10%. So we're trying to measure really quite low levels of opacity using our analyzer. The way the Model 4500 works and the way most other modern opacity monitors work as well is actually to use a double pass measurement. So we have the light source and both the light source and the detector are on the same side of the stack, and we use a passive reflector called a retroreflector on the other side of the stack. So the light crosses the stack twice, which doubles our sensitivity and makes it much easier to measure these very low levels of opacity. It also allows us to simulate a clear path condition by placing a reflector in front of the analyzer and blocking the beam and returning the light before it passes through the stack gases. So we can simulate a clear path condition quite easily using a motorized reflector, and that's what we do typically once a day on the Model 4500. So why are we measuring opacity? Well, in most countries there are regulations which govern the amount of smoke that's allowed to be emitted from a stack. In the US, the Clean Air Act requires process operators to demonstrate compliance with the relevant rules, and these are generally called New Source Performance Standards, which are performance standards that have to be met by any new source of pollution. These standards are specific to the industry, and they will typically have be referred to as the subpart of whichever act they are referring to. So, as I recall, power plants are in subpart D. These rules are written and enforced by the EPA. The rule for opacity monitors is a performance specification 1, and that states that opacity measurements have to be made using an instrument which meets the requirements of an ASTM standard, ASTM D6216, and that standard requires opacity monitor manufacturers to meet a set of specifications for linearity, temperature drift, and so on, to test the instrument according to the standard, and to provide a test report known as a Manufacturer's Certificate of Conformance, MCOC, to the plant operator. The operator, in turn, must purchase an opacity monitor, COMS Continuous Opacity Monitoring System. So they have to purchase an opacity monitor that complies with the STM standard. They have to install it in accordance with PS1. They have to complete post-installation testing to demonstrate that it's been installed and is functioning correctly in accordance with PS1. And then they have to report the opacity corrected to the stack outlet value so that it can be compared with the Human Observer's Method 5 assessment. Now, the STM standard, the STM D6216, is a consensus standard, and it was written by a group of users and manufacturers. I'm on the committee which wrote it and which has to review it every 5 years. The requirements of D6216 are that the analyzer must meet the defined performance standards and that the manufacturer has to test and report conformity with that standard. The testing is actually the responsibility of the manufacturer. So according to D6216, there is no third-party testing required. Now that's the US regulation. In Europe, compliance emissions monitors do have to be third-party tested. So the 4500 Mark III was tested in Germany by the TÜV organization, and we have a test certificate and a test approval according to EN 15267. So the instrument has been approved in Europe. So we have both the self-certification that's required in the United States, and we have third-party approval in Europe. The certificate of conformity that we produce for the ASTM standard is about a 30-page document, so it's got some very detailed test results. And this is the typical cover of the CFC. And it lists things like temperature tests, linearity tests, sensitivity to misalignment. So it's a very thorough test of the suitability of the instrument. Okay, next question. Where are we measuring opacity? Well, according to PS1, you have to measure the opacity using a light beam that passes through the centroidal area of the stack. That's the 1% area right in the middle of the stack. So you're getting a representative sample of the entire stack. And ideally, the analyzer has to be installed at least 4 stack diameters downstream of any disturbance. And that's to ensure that the stack gases and the particles they contain are well mixed at the measurement point. So we're not biasing the measurement by measuring in a non-ideal location. If that's not possible, there are some more specific rules. saying what you have to do if you measure in a less than ideal location, for example, less than 4 diameters after a bend. And the illustration here shows that we have to measure in the plane of the bend, not across the plane of the bend. And that's because the particles will tend to be moved towards the outside of the stack. So if you measure in this plane, you're still measuring all the way through the particles in the stack. Whereas if you measure in the perpendicular plane, you may miss a significant number of particles. So who needs to make the measurement? Or to put it another way, where do we sell the analyzers? A large number of industrial processes have to report opacity. And here's a list of some of them: utility electric generators, industrial boilers, electric arc furnaces, wood products, pulp and paper manufacturers, and brick kilns. Just before we go on with that, I'll unmute again and see if anybody's got any questions about
The conference has been unmuted.
Do we have any questions? Okay. I hope that means everybody's understanding everything, so I think that's good news.
The conference has been muted.
I'll go on to give you a little bit more detail on the applications I've just mentioned. Power generation, we went through in some detail earlier on in an earlier slide about how a power plant works, or in a little bit of detail at any rate. In general, the emission limit value applies to the stack. So the users have to report the opacity measured in the stack and report the opacity of the gases which are exiting into the environment. In a lot of cases, each boiler will have its own stack, or at least have its own flue within the stack. But particularly in some older power plants, you've got the situation that's illustrated here, where we have two separate ducts, each leading to a common stack. So the emission limit value will apply to the stack, but the process operator generally wants to know how much of that opacity is coming from each of their boilers and from each of these ducts. So here's a nice illustration of where we might need to install multiple analyzers on the same process. So we would have a compliance opacity monitor, the 4500 Mark III, on the stack, and non-compliance monitors for process measurements on each of the flues. And the nice thing about the land products is that the 4500 Mark III and the 4200 Plus share a lot of common components, so that circuit boards, detectors, and so on, and power supplies can be interchanged between the 4200 Plus and the 4500 Mark III. So only one spares holding is needed, even if they've actually got the two different products. Larger industrial boilers also need to report opacity. In the US, typically anything with a flue of 3 feet or 1 meter in diameter or larger will have an emission limit value. And some smaller processes also have to report opacity. We actually installed 4500 Mark III on an incinerator flue which was 10 inches diameter, 25 centimeters. So that's the smallest flue we've ever measured on. So there's a lot of industrial processes with boilers where opacity monitoring is a legal requirement. These boilers can be used to produce steam for the industrial process. Sometimes they're used for site heating. Hospitals and universities, for example, can have boilers. We've got opacity monitors installed at a number of universities. So there's a lot of processes like that where we need to measure opacity. Electric arc furnaces used in steel making are also users of opacity monitors. These in an electric arc furnace, scrap steel is melted to purify it, so all impurities and other components can be removed as slag, and then the steel can be recycled and used just as fresh steel will be. Electric arc furnaces generally have very low emission limit values, and so a very high quality opacity monitor is needed for these. And the 4500 Mark III is ideal for this because it has got a very low detection limit. It has a very good linearity, and its calibration and error test is generally very accurate. So it works very nicely on electric arc furnaces. We sold quite a few to wood products manufacturers. In wood processing, it's quite common to steam the wood to make it more pliable and easier to process. So what happens is the scrap wood from the process is burned in a boiler to produce this steam, and emission limit values apply to the wood boiler, and so opacity monitoring is used to measure the emissions there. Another application for wood is in pulp and paper. This is a significantly more complex application where the wood is basically digested to produce wood pulp, which can then be used in the manufacture of paper and paper products. The chemicals used to produce the pulp are then recycled in the waste heat boiler, and the heat is extracted and used to drive the process, and burning what's known as black liquor. And the emissions from the liquor boiler or from the recovery boiler rather, are regulated, and opacity measurement is required. Those are just some of the processes where we've installed opacity monitors. There are quite a few others, but those are some of the most common ones. So moving on to specifying the analyzer and discussing the specifics of the 4500 with a customer. The basic parts of the analyzer, the key components, are the transceiver and the retroreflector. These are where all the optics goes on. The transceiver shines a beam of light across the stack to the reflector, which returns it, and the detector in the transceiver measures the intensity. And in principle, it's a very simple process. We compare the intensity with the process in operation to the intensity measured in the lab at the same path length, which defines our 0% opacity clear path condition. The transceiver and retro and the standpipes they mount on are really the only absolutely essential parts of an opacity monitoring system. Now, standpipes are required because the optical alignment of the transceiver and retro is done by adjusting the tension of the bolts on the standpipe. So the instrument can't be mounted to a standard ANSI flange, though we do offer adapters that allow our standpipe to go onto an ANSI flange. The transceiver runs from 24 volts DC and produces a limited range of outputs. So the AFU, auxiliary function unit, APS, auxiliary power supply, and I/O module, AFU APS I/O, which is this white box here, is usually specified, and it takes mains power in and produces 4 to 20 milliamp outputs. It produces multiple Modbus outputs. It accepts inputs from blower pressure switches and so on. So it's generally used in all but the most low-cost installations. And it communicates with the transceiver using a pair of cables, one of which carries power, and the other is an RS-485 Modbus signal. Next item that is required is the air purge blower. Stack gases are hot, they're corrosive, and they're dirty. The 4500 Mark III is an optical system, so it's got lenses and delicate optical components, and we have to protect these from these nasty stack gases, and we do that by providing purge air, quite a large volume. It's 18 cubic feet per minute on either side, which, as I recall, is about 60 cubic meters per hour. So you can't really provide that amount of air easily from standard instrument air or compressed air supply. So we do recommend using a blower for the air purge. And if the blower were to fail, which is unusual, they are very reliable devices, but if the blower fails and the process is operating, the stack gases will cause some damage to the analyzer. And that will happen fairly quickly. So we offer fail-safe shutters which isolate the analyzer from the process if the purge air fails. So that's the next component in our system. And the last item, which is required by the EPA nowadays, is what we call the External Zero Device, or EZD. It's also known as a clear stack simulator, and it can be attached to the instrument to do two things. First of all, it verifies the zero reading of the instrument, which is why it's known as clear stack simulator. And it also allows a simulated zero condition so that the instrument can be audited using standard traceable reference filters. And once a quarter, to comply with EPA rules, users have to install the external zero device and make a series of measurements using traceable calibrated neutral density filters to demonstrate the linearity and the continuing accuracy of the opacity monitor. Are there any questions on
The conference has been unmuted.
Okay, I will carry on.
The conference has been muted.
In order to set up and configure an opacity monitor, there's a few things we need to know. First of all, we need to know the hardware that the customer actually requires, but we also need to know a number of things about the installation so that we can configure, focus, and calibrate the analyzer. And we do need this information with the order. So the first thing we need to know is the stack flange-to-flange path length. And that is the distance between the flanges mounted on the stack. The second thing we need, and we can calculate this based on the flange-to-flange path length in most cases, is the installation path length. And that is the distance between the front flanges of the transceiver and the retroreflector. And that is generally equal to the stack flange-to-flange distance plus the size of any accessories that are going to be installed. Accessories such as flange adapters, fail-safe shutters, anything that goes between the stack flange and the instrument. And that's the distance where we actually set up and calibrate the analyzer. And an error of 1% in that installation path length will generally result in an error of approximately 1% opacity. So it is important to get this path length accurate. The ASTM D6216 allows an installer to install an opacity monitor where the dimensions are wrong by 2%. So if it's a 20-foot path length, you need to be accurate to 0.4 feet, which is about 4 inches. But a question there, do natural gas utility boilers require opacity measurement? The answer to that question is no, they don't. The assumption is that there is no particulate matter in natural gas, and so the opacity should always be 0. The only circumstance where a natural gas boiler would require opacity monitoring would be if oil or very rarely coal were used as a backup fuel. So Opacity is most often required in coal-fired plant, but oil-fired boilers also require it, but generally not gas. Okay, back to our path lengths. The last thing we need to know is a factor called the path length correction factor. And this is the ratio of the stack size where we actually make the measurement, which is called the measurement path length, and the stack diameter at the exit. Now, if you go back to the method 5, the visual observation where the trained observer stands at the bottom of the stack, they're looking at the opacity at the stack exit. So for traceability to that, we must apply a mathematical correction to our measured opacity in order to report the stack exit opacity. And that mathematical correction is called the path length correction factor. I apologize, I've been talking about method 5. It's actually method 9. Method 5 is a different method altogether. So path length correction factor is the ratio of the measurement path length to the stack exit path length. So in this example, where we have a tapered stack, the PLCF will be less than 1. And that's probably the most common cases are either a straight stack where the PLCF is equal to 1, or a tapered stack where it's less than 1. We do occasionally get customers who install the opacity monitor on a duct leading to the stack. And in that case, the stack exit diameter is greater than the measurement path length, and the PLCF is greater than 1. The most common reason for installing on a duct is because they're low down, they're close to the ground, and it's easy to access the monitor for maintenance. And that is actually quite a good reason to install it there. One of the points I like to emphasize to our customers is that any instrument requires some maintenance, and maintenance is much more likely to be done competently and regularly if the instrument is placed in an accessible location. If the only way to access your opacity monitor is to climb a 100-foot vertical ladder, it's much less likely that the technician is going to take the time and effort to go and do that. A few other items that are useful and are commonly specified. Calibration stands. The US EPA no longer allows an opacity monitor to have a zero calibration done while the stack is not operating. So you've actually got to take the instrument off the stack and set it up in a clean laboratory at the correct path length. And so the calibration stands allow you to do that conveniently and easily. And they come complete with a power supply. So all you need for the laboratory recalibration is a calibration kit. And in the US, opacity has to be the opacity monitor has to be re-zeroed once every year. And customer has a choice of either doing that using the external zero device that I talked about earlier, and that can be done 2 years out of 3, or they can take it down every year and do it in the lab. And one thing I haven't emphasized today is that in the US, the usual reporting parameter is percent opacity. It's the optical characteristic of the stack gas. In Europe and in much of the rest of the world, the environmental rules are written in terms of milligrams per cubic meter, the actual mass of dust measured, the mass of dust emitted. And in those cases, there's an additional step that has to be taken. In addition to measuring opacity, that opacity has to be converted to the dust concentration. And the 4500 Mark III can do that calculation. It uses a parameter called the dust gain. But determining the dust gain requires a calibration relative to a reference method measurement, which is quite a complex procedure. And that's not something I'm going to go into in more detail here. Okay, last few slides coming up. So why would customers choose the 4500 Mark III rather than another opacity monitor? Well, first of all, we have over 20 years opacity experience, so Land has a lot of expertise in opacity measurement. Unlike some of our competitors, the 4500 Mark III has no continuously moving parts. The only moving parts at all are the zero and upscale devices, which move once per day to do a calibration check. We can support the analyzer fully from our base here in Pittsburgh. So we have expertise both in service and repairs, and we keep a full stock of spare parts right here in Pittsburgh. So anywhere in the US, we can generally supply spare parts overnight. We do have patents on our technology. There are several aspects of the 4500 Mark III which emphasize the stability and lack of drift, where we have techniques which we have patented. The instrument does come with a 3-year warranty, so we know it's a reliable instrument, and we put our warranty behind that. And the light source, which is an LED, green light emitting diode, has a lifetime warranty. We don't ever expect that to wear out. In the more northern parts of the region, temperatures can get very low. So minus 40 degrees C specification is standard. And for customers in the US, we can offer 2-week delivery for an urgent order. We do hold a complete system here in Pittsburgh. Generally, we would quote 4 to 6 weeks delivery, but we can improve on that if necessary. And unlike many of our competitors, the 4500 Mark III has actually been designed for easy maintenance. You don't need specialist tools. There are very few delicate components. So maintenance is really easy. So if you ever have to work on one, that has been taken into account. Whereas it seems clear from some of our competitors that they really don't want anyone other than their own engineers working on them. I've got a question from Patrick Peters. Does waste material incinerator operated only periodically have compliance requirements? In general, any plant which is subject to compliance, any category of plant which is subject to compliance reporting does have to report its emissions when it's operating. So even if it only operates periodically, it will probably have an emission requirement. Now, for waste incinerators, they are sometimes subject to opacity rules, and sometimes they are subject to PM, mass emissions rules. And what we've found in the US is even though the 4500 Mark III will measure mass emissions of particulate matter, and we do sell it for that purpose in Europe, US customers are generally reluctant to use an opacity monitor to measure PM. So it depends on what the emission rule, the suitability of a 4500 for a specific application does depend on the rule, and especially for incineration, that's worth checking. Okay, and right at the end, so far I've mainly been talking about the 4500 Mark III, which is certainly our most widely used opacity monitor. But we do also have the 4200 Plus, which is significantly less expensive and simpler. It doesn't meet the requirements for a compliance opacity monitor, but it is really just as accurate as the Mark III under most circumstances, and it's used for non-compliance and process measurements. And it's basically consists of the same main components. It's got a transceiver and retro, standpipes, purge blower. It's got a simpler power supply than the AFU APS. We call it the APS 42. It goes together as a very nice package for process measurements. So why would customers want the 4200 Plus? Well, it's based on the Mark III. It has absolutely no moving parts. The calibration checks that we have on the Mark III are not present on the on the 4200 Plus, so it's very, very reliable. As with the Mark III, we can support it from Pittsburgh. It has many of the same patents applicable, so many of the same technological advantages. Operation to -40 Fahrenheit is standard, and it's even easier to maintain than the 4500 Mark III because it's simpler. And we've got a nice application, just to wrap up, nice application for 4200 Plus in anode baking, which carbon anodes are used in aluminium production, and these have to be baked for a period between 24 and 36 hours to drive off volatile components. And opacity is used as a measure of the progress of that baking cycle. So by measuring the opacity of the emissions given off during the anode baking, the process operator has an indication of how well that's going. So we sold quite a few for that application. And so if you come across opportunities there, then by all means, 4200 Plus is ideal. So that's all I've got for this morning.
The conference has been muted.
If anyone has any questions, please go ahead.